Hi and good day. Today we'll be looking at grade 11 physics SPH3U, and the topic at hand is Kirchhoff's laws. These laws are two in number, and they're very interesting and they're very exciting, and it really allows us to solve circuit problems quite easily. So before we delve into that material, we just need to have some recap. Firstly, we'll go over some common circuit symbols, the first of which is a battery. So a battery is written as two parallel lines where one is longer than the other. The longer side is the positive pole and the negative side is denoted by the shorter line. Secondly, the symbol for a resistor. Resistor can be a rectangle or a jagged line, as you can see in the pictures. So we have a wire entering the resistor and a wire leaving it. The second thing we need to recap is how current flows around the circuit. When we think about current, we think about the flow of electrons. That's how current works. And if we think electrons, we think, okay, the negative side of my battery, electrons has to flow from, so current starts there. However, in historical times, current was always believed to emanate or leave from the positive side of the battery, go around the entire circuit, and come back into the negative side. So instead of changing notations and whatever, we decided up till today to keep this flow of current where it goes from the positive side of the battery all the way to the negative side. This is known as the conventional flow of current. And we will apply this conventional flow to all circuit problems. The third thing is Ohm's Law. So Ohm's Law states that the current through a conductor between 2 points is directly proportional to the voltage across these 2 points. So first of all, a conductor. A conductor means that current flows easily through it. There's minimal resistance. So all metals are conductors. That's why you don't stick a metal fork into the electrical socket. You'll get shocked. It conducts the electricity. The inverse of that is an insulator, which doesn't conduct as well or not at all. That is like plastic. Ohm's law is commonly known in its famous formula, V equals IR, where V is the voltage across some component, say a resistor, I is the current across this resistor, and R is the resistance of the said resistor. So now we can tackle the crux of the matter, which is the current law and the voltage law. So Kirchhoff's current law, KCL, states that the total current entering a junction must be equal to the total current leaving that same junction. So if you watch our diagram here, our junction is denoted by that black dot. That means those 4 wires are connected there. So a junction means that 2 or more wires are connected at some point. If that black dot wasn't there, then those 2 wires would just be resting on each other. So if I notice I have 2 currents coming in to the junction and 2 sources of current leaving that junction. The total current entering that junction then is I1 plus I2. And the total current leaving that junction is I3 plus I4. Thus, the total current in equals total current out, which implies I1 plus I2 is equal to I3 plus I4. A nice thing of KCL is that it maintains the conservation of charge, which means that current doesn't magically appear or disappear. So whatever current goes into that junction, you can bet $100 that current has to leave that junction. The charge is conserved. The second thing here, or the second law I should say, is Kirchhoff's voltage law. So Kirchhoff's voltage law says that the algebraic sum of all the voltages around a closed loop is 0. Closed loop means that you have a connected circuit. There's no gaps, there's no breaks. So if current leaves the positive end of my battery, goes around the circuit easily, and it comes back to my negative side of the battery. That is a closed loop. It is a closed circuit. Now, when we talk about this, we have to understand that some voltages can be positive and some can be negative. And this all depends whether the components in your circuit experience a potential gain or a voltage gain or a potential loss, also known as a voltage loss. So if you watch this diagram, our current leaves from the positive side of our 45 volt battery. It goes by the corner 2, makes a right turn, and then it goes towards resistor 1. Now because we are going with the direction of current, the conventional flow of current, where the current enters the resistor, that becomes positive. And where that current leaves the resistor, that becomes negative, as shown in the diagram. So this resistor R1 will experience a voltage drop, denoted by negative I, which is the current going around the series circuit, multiplied by R1. So that is a voltage drop. If we were going the other way, it would be a voltage gain. It would be positive IR1. An easy way to remember this is that where my current leaves my component, it takes that sign. My potential takes that sign. So here it's negative, I get a potential drop, so it's negative I multiplied by R1. So let's take the current law and voltage law and apply them to this circuit. So it looks okay, parallel circuit, 2 power sources, 3 resistors. Let's use the laws because it makes the calculations so much easier. First thing we do is that we identify the junctions. We have 2 junctions, A and B. We can see that by our black circles there. So when we think junctions, we think, okay, KCL or the current law has to come into play. Surprise, surprise, that's what we do next. So let's take some power source, E1 say, and we have some current I1 leaving E1. So we leave E1 and we go towards junction A. So that means my current has to split. So on the upper branch of my circuit, I have a current I2, and on the lower branch of my circuit, I have a current I3. So by Kirchhoff's current law, I know that I1 is equal to I2 plus I3. If we follow these currents and we come back to junction B, again I2 and I3 are coming into the junction and I1 is leaving that junction. So by the current law again, I2 plus I3 is equal to I1. Same relation we had at junction A. The third thing is to label all possible closed loops. So in our diagram, we have 2 of them. On the first half, the upper half of the circuit, we draw our loop going clockwise and we label that as 1. And at the bottom half of the circuit, we draw our loop going counterclockwise. We label that as loop 2. What these loops mean is that this is how we will walk around this circuit. So we will walk around this circuit and see how current interacts with the resistors, or how current interacts with the power sources E1 and E2. So let's look at loop 1. And we start at junction A. So we're going counterclockwise, so basically we're following the route of I2. So we're going, we go up with I2, we make a right turn, then we hit R1. But because we are with the flow of current, there will be a voltage drop here, potential drop. So this becomes negative I2 multiplied by R1. Okay? And then we continue again, we make a right turn, we come back down to junction B, we make another right turn, and now we reach R2. Now what we've seen even from before, at junction B we have KCL. So now I2 is flowing in this middle branch of our circuit. But again, we're in the flow of I1. So the current will interact with R2 in such that there is a potential drop. So we get negative I1 R2. After we leave R2 and we're going leftwards towards A, we hit the power source, the battery E1. The battery will go from the negative to the positive. So at the end is positive, so we get a voltage gain, plus E1. So those three quantities must be equal to 0 according to the voltage law. That's equation 2, what we see there. Similarly, let's start from A and go downwards, counterclockwise, following the loop. Again, we follow I3 because that's the direction of our counterclockwise loop. We reach E2, that's negative to positive, so that's positive E2. We go to R3, sorry, okay, then that's a potential drop, so negative I3 multiplied by R3. We go up to junction B, we make a left, and again we're with the flow of I1, so we get another potential drop, negative I1 multiplied by R2, and then finally we hit the negative side of E1, and we go to the positive. So positive is the last pole, so we get positive E1 as we come back to our starting point at junction A. So now we have three equations and three variables as seen in this slide. And if we have values for R1, R2, R3, E1, and E2, then we can solve for all our currents. So what we'll do in the next slides is just show calculations of how we calculate all of these currents. So we can add equations 2 and 3 and we get a relationship where we see we can have I2 expressed in terms of I3. So we do that. We get I2 is equal to 300 I3 minus 4 divided by 100. So then we can take this quantity of I2 and we can plug it in back to our second equation. So recall, the second equation is written as negative 100 I2 minus 200 I1 plus 3 is equal to 0. I2 we just found, so we can replace that in. And then when we look at negative 200 I1, we know, hey, I1 by current law is equal to I2 plus I3. So we sub that in. And in the third line, we sub I2 for the value of I3 that we've just found in the previous slide. So our final equation here only has one variable, I3, and we can solve for that. So solving through, we get that I3 is equal to 3 over 220 amps. We know we have a relationship linking I2 and I3. We solve for I2 using that relationship. Then we solve the system, we get 1 over 1100 amps. And then finally, we know that I1 is equal to I2 plus I3. We found I2, we found I3. So now I1 is equal to the sum of those two quantities, which equals to 4 over 275 amps. So in conclusion, the procedure to use these current laws and voltage law in any circuit is that 1. Label a junction. 2. Choose your power source. 3. Start conventional current from that power source. 4. Apply KCL at junctions. 5. Identify all closed loops. And 6. Choose the directions that you want to go around these loops and apply the voltage law. Two final things is that you want to solve a system where the number of equations is equal to the number of variables. So if I have to solve for 3 currents, then I would want to have 3 variables. Then I get distinct solutions. And the last point is really important, is that if I'm going around the loop in a certain way, I'll show it here in the previous slide. So say for example, I was going clockwise with loop 2. Then I would be going against the flow of current into R2 because I1 is going right to left, but my loop is going left to right. So what happens is that will become a voltage gain. It becomes positive I1 R2. Hope that helps, and thanks for watching.